talking about the common ion effect and sort of again what that sort of means. It's very similar to the idea, obviously, of what happens with Le Chatelier's principle. So, in the common ion effect, what happens is, again, with that weak acid or that weak base, we basically get it to be kind of suppressed. And basically, what that means is it's really not going to break apart like it would if that sort of common ion was not present. So, if we looked at acetic acid, which is obviously a weak acid, and by itself, sort of, in a beaker, if you will, right? It will go in and it will, set up that equilibrium basically. And, we'll have both of those things really floating around kind of in the solution. Now, it's going to break apart and produce a certain amount of H plus in this particular case. But if we actually threw in there with our acetic acid, we went to the shelf, we grabbed off the shelf maybe some sodium acetate, which is just a salt. And because it's a salt, it will break apart into sodium ions and acetate ions. And it is that acetate ion that is really the common ion here. So when we would throw that into the mix here, we're going to have some sodium ions, which really aren't doing very much of anything, but we are going to add some acetate ions into our beaker. That is going to really cause the Le Chatelier's principle effect to come into play, because we are essentially adding more of our acetate here to the right-hand side of the reaction or equilibrium. We would expect it to force the equilibrium to head towards the reactant side. And what that's going to do is a couple of things. It's going to, as it mentions here, suppress basically the ionization of that weak acid. And basically what it's going to do is keep this thing together pretty much in solution. So as it kind of pushes the other way in this equilibrium, what we're mainly going to have kind of floating around in that solution, is the acetic acid all still together. What does that mean, in relationship to, say, pH, since we've been talking kind of about pH and acids and bases? Well, what that means is if we are shifting the equilibrium to the left, we're going to have less H plus present because it's going to kind of be shifting over there to the left. Less H plus present will have an effect on the pH, right? So we'll have less H plus. Less H plus means that we would expect the pH to go up. And in relationship to where acetic acid would be by itself. So in relationship, acetic acid in the beaker by itself would have a certain amount of H plus. This presence of the sodium acetate that was added to it is going to basically suppress that and keep the acetic acid together in this example. That's going to relate in a less amount of free H plus. Remember that pH is really related to that. The pH is related to how much free H plus, basically. How much in the beaker or something, how much free of these guys, not attached to anything, free H plus is basically floating around in the solution. The greater the amount of H plus, the lower the pH, right? And vice versa. So by having this common ion effect, it makes the weak acid and also the weak base as well basically stay together. The result of it with a weak base is kind of the same idea. Instead of, in a weak base situation, something like this, perhaps. Maybe you throw in some ammonium into this, ammonium nitrate or something into this solution. Going to force the equilibrium back this way. What does that do with the hydroxide concentration? Well, it lowers the hydroxide concentration. When it lowers the hydroxide concentration, the H plus concentration basically goes up, right? Because they're tied together, right? As the H plus goes up, OH minus goes down and vice versa. So by lowering that OH minus, it will technically increase the H plus. And in a normal sort of basic weak base, we would have, say, a pH up here in the basic range. And with that common ion present, it may not get to acidic, but we would expect it to sort of come down in terms of the pH in that particular case, because again, it's suppressing really the amount of hydroxide in that solution. Questions on common ion here. So it really is sort of Le Chatelier's principle sort of playing out in the presence of that common ion. And it's actually a pretty good application of this is, as we will see here very shortly, is basically this is, what really makes a buffer sort of function, and why a buffer functions like it does is this sort of effect. And on the bottom is pretty much what we just talked about up there on top. Again, forcing that equilibrium to the other side, keeping the H plus not as free in solution. All right, so take a few minutes here, finish up part A here, which is just calculating the pH of a solution, 0.2 molar acetic acid, Ka value on the bottom, and we'll talk about it. And then obviously we will tackle part B, which is a more common ion type problem, and I'll kind of show you what's going on in that. So take a few minutes here and finish up A, and we'll talk about, where you're at on that. So let's take a look at part A here and see what's going on with it. Really, this is just like we've done before. This is really just a weak acid problem. We have just the acetic acid by itself. So we would proceed to do this problem like we would do a normal Ka type problem. So here we would take our acetic acid. We would let it dissociate into H plus and acetate. And in this particular case, I believe we are starting with 0.2 molar of that guy, 0 and 0. Change would be minus X, and plus X, which means when we reach equilibrium, we have 0.2 minus X, X, and X. Any questions on the ice table here? Okay. So just like before, this will go into our Ka value, which they gave us, which is 1.8 times 10 to the minus 5. And that would obviously be our products over our reactants. So putting those guys in gives us x squared over 0.2 minus x. We've been doing good with the assumption, so we're going to assume that x is equal to 0. That will give us x squared divided by 0.2 is equal to 1.8 times 10 to the minus 5. We're going to multiply the 0.2 to the other side, also do a little square root action on that. So we will end up with, looks like we end up with an x value of, we'll call it 1.90 times 10 to the minus 3. We do want to check it, so we'll divide that by 0.2. We'll times it by 100 to check it, and I think it's like 0.9%, so I think our check is good. That x, like we've been doing before, will equal the H plus concentration, which is what we need to calculate the pH. So our pH would be minus the log of our 1.9 times 10 to the minus 3. And that would give us, for this solution here, looks like a opening pH here of 2.72. Any questions on any part of that calculation there? Now, what this really represents is this represents the pH of our solution here of just acetic acid, where it goes for a swim, and it basically sets up that equilibrium all like it naturally will. And this solution here would have a pH of 2.72 if you dropped like a pH meter in there and took the reading. So what we're going to look at here in the second part of the calculation is what is the effect really going to be if we sort of introduce a common ion to the mix here. So instead of just having our acetic acid like it is there in the beaker, we're going to add really some sodium acetate to it. So let's see how that sort of affects this calculation and sort of how you should approach this calculation. So in part B, I guess there we have a solution that is 0.2 molar acetic acid and 0.3 molar sodium acetate. And we're looking to see what the pH, obviously, of this solution is. We still have the same Ka value as we used there in the first part. So between these two things, you know, what is going to happen in this reaction when they're both in there together? Well, we first should analyze kind of the two things that we got. These two things are related to each other, obviously. We have acetic acid, which is like a weak acid. We have sodium acetate, which is kind of like a conjugate base. But between the two, it is only going to be the acetic acid that will set up the equilibrium. This is really a salt, right? And that salt is going to 100% break apart into ions when it goes for a swim. So what that means is out of these two guys, the sodium acetate is going to, again, 100% break apart into sodium ions plus some acetate ions floating around in there. So when we think about sort of what we should be looking at in terms of the equation we use for our ice table, what's going to set up the equilibrium, we should be looking at the acetic acid because it's a weak acid. And again, it's going to be the one that's going to be able to set up that equilibrium. How do I know that? Well, same things we knew before. I have a Ka value for acetic acid, tells me that's going to be the weak acid and the one setting up the equilibrium. So in terms of the concentration, though, of these ions, it is a one-to-one relationship between the sodium acetate and the sodium ion, which means its concentration would be 0.3 molar. It's also a one-to-one relationship between the sodium acetate and the acetate ion, which means the acetate ion here would also have a concentration of 0.3 molar. So what we're going to start with is an ice table. And again, out of those two, it is only the acetic acid setting up this equilibrium. It will look very much like the one we just did on the previous part of the problem. Now, initially, we have 0.2 molar of our acetic acid. We have 0 of our acid, 0 of our H plus. But the important part here is the acetate. We actually do have an initial amount of it being supplied by the sodium acetate. So to turn this into a common ion calculation, you do need to include the initial concentration of your acetate. Obviously, if you do not include the initial concentration of your acetate, you pretty much just did the same problem we did in part one here. So it'd just be a weak acid. So that is something when people do ice tables in a common ion situation, which as we'll talk about is really a buffer situation. It is the thing that is most commonly messed up by people is they will do a 0 there on the right-hand side where the 0.3 is because they're so used to putting zeros, and you will get the wrong answer because you're not doing the proper calculation there. you're doing a weak acid calculation by not putting a number there. So by putting the number there, that implies that we have some acetate to begin with, which is what's happening in this situation. And that's going to obviously affect not only the calculation, but the result that we get at the end. So let's continue on and see the rest of this. The rest of this is pretty much like we just did. We're just going to do our x's. So minus is on the left, plus is on the right. We end up with 0.2 minus x, x, and 0.3. Other very common mistake, this is plus x, not minus x. Again, people very common with the minuses with x and stuff, so especially with a number involved, but that is plus. Just like we did before, we're going to go into our Ka expression, and that's going to give us x times 0.3 plus x divided by 0.2 minus x. And that is going to still equal the same Ka value that we've been using, because we're still really looking at acetic acid here, which is 1.8 times 10 to the minus 5. At this point, we're going to assume that x is equal to 0. Again, a reminder that you can't get rid of, obviously, all the x's, otherwise you have nothing to solve for. So just the x's we're adding are subtracting from a number are the x's that we're going to get rid of. And when we do that, that reduces this down to basically x times 0.3 divided by 0.2. And that's going to equal 1.8 times 10 to the minus 5. We're going to obviously multiply the 0.2 to the other side and come back and divide by the 0.3. And if we do all that good stuff there, yeah, it looks like we end up with an x value of 1.2 times 10 to the lot of zeros. We're going to go with 1, 2, 3, 4, 5 minus 5. We obviously made our assumptions, so we want to double check it. So we'll take it and we'll divide it by 0.3 times it by 100. It's not even 0.1%. So the check here is good. That again means in this case that that would be our H plus concentration, which means we now can go into our pH, which would be minus the log of the H plus. And that would give us minus the log of 1.2 times 10 to the minus 5. And that will get us a pH of 4.92 in this case. Question on any part of that calculation there? So the question is, when doing the check, how you know which one to divide by? Truthfully, you should technically divide by, the question is, should you divide by 0.3 or the 0.2? Technically, you should divide by both. In practical application, probably if you divide by one of them and they're okay, the other one's probably okay as well. But you actually could choose either one. And you should, I guess, technically kind of do them both. But in my experience, usually if one of them's okay, the other one's probably okay as well. But if you did it with, for example, the 0.2, it's also not even 0.1%. So in most cases, you'll usually be okay. But you should at least check one for sure. If you got the time, check them both. But like I said, I'd probably think in most cases, if one's good, probably the other one's good as well. Other questions on that? So what's happening here? So let's think about sort of what is happening in this situation. Again, we have our wonderfully drawn beaker here. And in this beaker, we threw in our acetic acid, which just like previously is going to set up that equilibrium that's going to keep all these guys really in solution. Right? We then dumped our sodium acetate in there, and again, that's really a source of just some sodium ions floating around, not really important as it's neutral, right? It's a neutral sort of part of the salt, but we have some acetate ions happening. And again, that acetate ions coming in from the sodium acetate is going to really increase the amount of acetate present, going to really cause these guys now to sort of combine is really what's happening here. There's a lot more acetate. It's going to go find some of that H pluses floating around. It's going to cause essentially this equilibrium to shift to the left. And we're now going to have a lot more of the acetic acid altogether. This is going to result then in less H plus. How do we know it's less H plus? Well, we see the pH at this point is 4.92. If we just go back one step here where we did not have the common ion, our pH was 2.72, much lower, right? And the reason our pH went up is because this situation right here, again, is happening with that extra acetate in that solution. It's going to do Le Chatelier's principle and kind of kick the reverse reaction into place. When the reverse reaction gets going, it's going to start gobbling up some of this H plus to reform our acetic acid. The result of that is what we see is the H plus concentration goes down. The result of that, as we see here, the pH ends up going upwards. Question on sort of what's happening here. Okay, so this is really, a common ion effect. This is essentially, as we will talk about here in just a second, really what's happening in a buffer situation. And one thing, if we sort of look at the numbers here in terms of this table, if we look at the concentration of what we started with in terms of the acetic acid and in terms of the acetate here, there we go. So if we look at the initial concentrations of those two guys, the acetic acid and the acetate, and if we put our X values back in to here to see really what we got going on at equilibrium at this point, what you will find is pretty much your initial concentration of this guy and your initial concentration of this guy is about the same as your equilibrium concentration. Again, if you put in for X in each of those cases, 1.2 times 10 to the minus 5, essentially that number doesn't change. It's basically the same number. So the nice thing about that is when we do have problems like this that involve common ions, and we're starting with concentrations which are relatively high or reasonably high, kind of like what we started with there in that particular reaction, we could almost forget about what is happening in terms of the change part because it's not going to be all that much. And we can basically use our initial concentrations as our final concentrations at equilibrium. Again, because of this common ion effect, there's going to be not a lot of change that's occurring. The nice thing about that is if we wanted to solve for the pH in a problem like we just did, we actually can not necessarily need to use an ice table. We could use what is referred to as the Henderson-Hasselbalch equation. And it's derived basically from a common ion effect. And all of this, that's basically how it's derived there on the left. Not that important. I'm not going to ask you to derive it or anything. But what's in the boxes are important. That is the Henderson-Hasselbalch equation. And that is that the pH is equal to the pKa value plus the log of the base over the acid. How do we calculate the pKa value? That is right there. The pKa value is equal to minus the log of the Ka value. So in a common ion problem, or really, as we will continue talking here in this chapter, a buffer problem, you could use this Henderson-Hasselbalch equation to calculate the pH, and you don't have to do an ice table. You basically could just go right into the equation, and you'll be good to go. Now, there is similar sort of formulas to the Henderson-Hasselbalch equation that does not measure pH. There's actually kind of a version that measures the pOH, and the pOH is equal to the pKb plus the log of the acid over the base. So there are a few differences here because this is more basic and sometimes used for basic buffers. We use the pKb for the base, and it's acid on top, base on the bottom. Why would you want to maybe use that? Well, you could do that and then obviously use your pH plus your pOH is equal to 14 and get your pH. Personally, by the way, the pKb value is found the same way, minus the log of the Kb value, just like the Ka value. Would you want to use this? Well, personally, I don't really see sort of the use of it in most situations because in most questions you're actually asked for the pH, right? So if you use this equation up here for a basic buffer, or basic situation, you still got to subtract the 14 to get to the pH. You might as well just go right into the Henderson-Hasselbalch equation, even though it's basic. It doesn't matter. You can use the Henderson-Hasselbalch equation for acidic, basic, whatever, neutral buffer, all those things could go right into here. And I just think that's probably the better move because in most cases, you're not a lot of times asked about the pOH, but you're really asked about the pH. But I'll put it up here so you've seen it. Again, it is different than the Henderson-Hasselbalch because, again, it's acid over base and pKb. But I would say always probably roll with this equation here. It can be used in all situations. And since most of the time you're looking for pH, that's probably the right one to use. Speaking of pKa and pKb, sometimes you might want to kind of go from one to the other. So there actually is a nice relationship between those two things. If you take the pKa plus the pKb, it equals 14, kind of like the pH plus the pOH equals 14. So, if you have a basic situation and you have a Kb given to you, you can calculate the pKb, subtract 14 and get to the pKa really quickly. And you could get into that as well. So again, that's another useful relationship that might pop up somewhere. But again, pretty much every time go with the Henderson-Hasselbalch, which again is the pKa value. So you want to make sure that's a pKa value plus the log of the concentration of the base over the acid. Question on that there. So you might ask, okay, how does this apply to, say, the question we just did previously where we did the ice table? Well, let's take a look at that question one more time. And let's approach it using this situation here. So we had 0.2 molar acetic acid, and we had 0.3 molar sodium acetate with a Ka value of 1.8 times 10 to the minus 5. Again, the recognition part of here that lets you know you can use the Henderson-Hasselbalch equation is that this is a weak acid. This is essentially its conjugate base. And that's really a buffer situation. And that automatically tells you, hey, I could use my Henderson-Hasselbalch equation, which is this. So to calculate the pKa value, we would go minus the log of the Ka. So that's going to give us minus the log of 1.8 times 10 to the minus 5. That's going to give us a pKa value of 4.74. Now we're good to go into the Henderson-Hasselbalch equation, 4.74, which is our pKa value, plus the log of the base. So again, understanding that this guy over here is the base tells us we should go with 0.3 up on top and 0.2 there on the bottom. And if you do all that good stuff there, lo and behold, we end up with 4.92 as the pH of this sort of solution. Again, just to verify with you what we saw when we did the last calculation. There it is right there. We ended up with 4.92. So this demonstrates two things. First off, let's get this out of the way. People always want to use the Henderson-Hasselbalch equation in every situation whenever they have two numbers. They're like, cool, I got two numbers. That's what I need for the Henderson-Hasselbalch. I'm going into it. You should only use the Henderson-Hasselbalch equation when it is a common ion problem, which is essentially, in most cases, a buffer problem. So it's a limited use of the Henderson-Hasselbalch equation. And it's a limited use of that Henderson-Hasselbalch equation. It does need to be a common ion type problem. Now, you can also use, obviously, the ICE table as we did here on the screen. And you can see that there on the screen, we use the ICE table, we use the Henderson-Hasselbalch equation, we get the exact same pH. So you can use the ICE table always. So if you're more comfortable doing the ICE table, you can still do the ICE table in a common ion problem like we did previously. You'll get the same answer. If you could recognize it as a common ion problem or a buffer problem, I might recommend using the Henderson-Hasselbalch equation because it can save you time. But again, as you can see, they both should really give you the exact same answer regardless of which way you go. So ICE table, you could always fall back on and kind of use it. Here, Henderson-Hasselbalch, again, should only be used in a specific situation where you have a common ion present, which is really buffer type problems. Any questions on that there? Okay. The important part again here is make sure pKa you're using and make sure base on top, acid on the bottom. And, you should know if we get the right answer. So why don't you take a look at one here and see what you come up with. So why don't you take a minute or two here. We want to calculate the pH of a solution that contains 0.3 molar formic acid with 0.52 molar potassium formate. Ka value of formic acid, 1.7 times 10 to the minus 4. So take a moment or two, and then we'll talk about it. Be looking for here in this problem. Well, we got a solution that contains 0.3 molar formic acid and 0.52 molar potassium formate. So they definitely look related to each other. We got a Ka value. This would be our weak acid. And this would really be our conjugate base here. How do I know this guy here is not the acid? Well, it's got a potassium, right? So this is really formate. This guy's got the extra hydrogen, which it needs to donate, right? That makes it the acid. So again, here we have two things that are really sort of related to each other. This is really a common ion sort of problem. Now, if you recognize that right off the bat, that means you can use your Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the base over the acid. Here, pKa value would come from there. So the pKa would be minus the log of 1.7 times 10 to the minus 4. That looks like maybe a 3.77 in terms of our pKa value. Now, that will go into our Henderson-Hasselbalch, which would be 3.77 plus the log. Again, understanding what you are looking at, really important here. So again, the base is going to go up on top, which would be the 0.52. Our acid would go on the bottom. And if we do that, 0.52 divided by 0.3, take a little log of it, add it to 3.77, looking like we're going to get a pH of 4.01 in this situation. First off, any questions on that calculation there? Now, let's say you weren't sure you should use the Henderson-Hasselbalch. or don't want to use the Henderson-Hasselbalch. Again, you could approach this ice table way, a little bit more work probably, but again, it's going to be the weak acid that's going to set up the equilibrium here. It's going to break apart into H plus and some formate. Initially, we would have our 0.3 molar, 0. And again, the important part would be right here. We do have an initial amount of formate coming from our common ion. Change here would be minus x, and at equilibrium, 0.3 minus x, and 0.52 plus x. At this point, obviously, you would go into your Ka, which would give you x, 0.52 plus x divided by 0.3 minus x is equal to 1.7 times 10 to the minus 4. You'll do a little assumption that x is equal to 0. That will get you x times 0.52 divided by 0.3 equaling our 1.7 times 10 to the minus 4. That is going to get us we'll call it 9.81 times 10 to the minus 5. We obviously would want to check it by dividing by, say, 0.3, times it by 100, and we're good to go, minus the log of our 9.81 to the minus 5, going to get us, again, the exact same pH as we got above, which would be 4.01. So you can see, by the way, we check is good. A little bit more steps to do to get you there, but it does get you there. You could also see this is a little bit more streamlined, if you will, probably a little bit more quicker. And again, why you probably should use the Henderson-Hasselbalch equation in these situations. But again, as the bottom also shows you, you don't have to do it. So if you, again, are more comfortable, like the ice tables, love the ice tables, you can do it that way. But again, I do caution you, like I did before, go crazy with the Henderson-Hasselbalch equation. Don't try to use it in every situation because you will get a lot of things wrong. So again, it's a very specific equation for a very specific situation. Any questions on that? Okay, so let's actually talk about then what is that really situation that you should use the Henderson-Hasselbalch equation in, and really what we're talking about in this problem and even the previous problem that we did. Really what we have going on in these problems is a buffer. And what is a buffer? So let's talk a little bit about sort of what a buffer is. A buffer really is a solution, first off, is made out of either a combination of a weak acid and its conjugate base, or sometimes referred to the salt of its conjugate base. Or you can make a buffer, as it says there, out of a weak base and the salt of its conjugate acid. So what does that mean? It means that both of them, like the little thing says there, is actually in the solution to start with. So you got both of those things floating around in the actual solution at the outset. So you got like an acid part of the buffer floating around, got like a base part of the buffer floating around. Why is it important that the buffer be made up of a weak acid or a weak base? Why is weak part of it important? Well, the weak part of it's important because it is a weak electrolyte, which means when we take something like acetic acid and you make a buffer out of acetic acid and sodium acetate, for example, that is a weak acid and its conjugate base. When acetic acid goes into solution, like we've been seeing, it will set up this equilibrium. And what is this equilibrium really doing? Well, it's allowing both of these guys to sort of be in solution at the same time. And that's how we get, like in this picture, the acid part, which would be like the acetic acid in this case, and how we get the base part of the buffer, which would be the acetate, in solution in a good amount of quantity to really be able to behave like a buffer. So what does a buffer do? Well, first off, there's a big misunderstanding sometimes about a buffer and what people think a buffer is. Sometimes people think a buffer is a neutral solution. And the answer to that is, well, it can be. But it could also be an acidic solution. It could also be a basic solution. So a buffer does not necessarily mean that the solution is neutral or have like a pH of 7. A buffer means that you have a solution that has the ability to resist changes in pH, even if you decide to add some more acid or base to it. What that means is it's able to maintain the pH. So, for example, if your buffer started at a pH of 4 and you add some acid to it, will it go down? It will go down. It'll go down a little bit, but maybe it goes from a pH of 4 to like a pH of 3.9 or 3.89 or something like that. If your buffer started at a pH of 4 and you added base to it, it's going to basically stay around 4. Maybe it goes up a little bit. Maybe it goes like 4.05, 4.1, something like that. But it will not jump, for example, your buffer, if it is a good buffer, if it started at a pH of 4, it won't jump to like, all the way down to a pH of 1 if you add acid, or it won't jump all the way up to like a pH of 12 if you added base to it. So a buffer is really able to resist those big jumps in pH. And one of the main reasons it's able to do that is because it's able to keep in solution really an acid and a base. And that's really important for how a buffer functions. So you may ask yourself, can you make a buffer that contains a strong acid or a strong base? And the answer is actually no. So the reason for that is, for example, if we look at something like, say, hydrochloric acid, which is obviously a strong acid, when it goes into solution, it's going to break apart into H plus and Cl minus. And you may say, well, isn't this an acid? And isn't this its conjugate base? And the answer is, yeah, it is. But the difference here between, say, acetic acid and our hydrochloric acid is when acetic acid goes into solution, it's a reversible reaction, which means it mainly stays here, but we do produce some of these guys. In hydrochloric acid, when it goes for a swim, we're producing 100% these guys and like none of these guys, which means when we think about sort of the buffer, the only thing we would technically have in that solution is a conjugate base, right? We wouldn't have the acid part that would be needed for a buffer to function properly. So what we would basically have floating around is H plus and Cl minus, right? And if you add more acid to it, you're going to add more H plus, and all of a sudden you got a lot of free floating H plus in that solution, and it obviously will see a big jump in the pH. So a buffer cannot be made up of a strong acid or a strong base. Because of that, they will 100% break apart into ions. They won't be able to keep really both of those things in solution to effectively work as a buffer. Any questions on that there? Now, this shouldn't be confused with something that we will see down the road here, is the idea that although you cannot have a buffer that is strictly made up of a strong acid or strong base, you could actually produce a buffer from a reaction of a strong acid or strong base. So you can actually make a buffer, but the buffer itself is not made up of the strong acid or strong base. What happens in that reaction, as we'll see later on in this chapter, when you react to strong acid, it actually, all the strong acid gets used up. It's no longer there. And if you happen to react a strong base, all the base gets used up. And the only thing you're left with, for example, is a buffer that's been made. That's a weak acid and conjugate base, or a weak base and conjugate acid. So a buffer cannot be made up of a strong acid or strong base. But as we will see a little bit later on in this chapter, you can actually produce a buffer from a reaction of a strong acid with a weak base, and vice versa. All right, so let's talk really though, how does a buffer really function to, prevent that pH from going crazy and jumping around and seeing these giant changes in pH. So let's start by talking first off about a solution that is not a buffer, and that is water. And we'll get there here in a second. There you go. So let's talk a little bit about water, which is not a buffer. And let's talk about what happens when we dump some, say, strong acid into water, like hydrochloric acid. So if I take some hydrochloric acid and put it in some water, as we've been talking about, it is a strong acid, which means it's going to 100% break apart into our H plus and Cl minus. So how is this going to affect the pH, right? Well, the pH is equal to minus the log of the H plus concentration, which means when I put this hydrochloric acid into water, which is not a buffer, it essentially is just going to let it do its thing. And it's going to produce a lot of H pluses, free floating around. We'll also have some Cl minuses. But most importantly, what we see here is we just produced a ton of free H pluses. We produced a lot of these guys. And how does that affect the pH? Well, if the concentration of H plus increases, that means we would expect the pH to go down. So for example, let's say our water had a pH of like 5.5. By the way, water is not necessarily neutral all the time. So let's just say, it has started at a pH of 5.5. We add some acid to it. This thing maybe drops down to like a pH of 1.1 or something like that. A very significant drop in the pH is probably what we're going to see here, because we have just produced a lot of free H plus very, very quickly. And you may say to yourself, well, it went from 5 to 1. Is that a lot? Well, it actually is. Every like pH change of 1 is like a power of 10 change, right? So there's a lot of H plus that pretty much went into that solution to cause that pH to drop by that much. So we see a big jump in pH here because water is not a buffer. It cannot handle all that H plus that's basically coming into the solution. And we see an increase in the H plus, a decrease in the OH minus in that case, and the pH starts to drop. What happens if we take a base and basically add it to our water as well? So what's going to happen in the base situation here? Well, in the base situation, let's say we took our sodium hydroxide and we added it to our water. It also is going to break apart into sodium ions and hydroxide ions. So what's happening here? Well, we see the same thing. It's going to be 100% going to be these guys over here. It's going to be produced. We will no longer have any of those guys together, just like up here, we had none of those guys together. But what we did produce on the product side here is a lot of free OH minuses in this case, right? And what does that mean in like a solution situation here, right? We will have a lot of these OH minuses floating around in the solution, all lined up nicely, probably not. But because we produced a lot of OH minus, and if you remember when we were talking about KW, as the concentration of OH minus increases, the concentration of H plus will decrease, and we would expect the pH to increase in this case. Again, the sudden influx of all that OH minus is going to cause a pretty big jump in the pH, again, because we've now got a ton of this free floating OH minus in the solution. So maybe the pH in this case, again, started at 5.5. Now with all that OH minus that came into the solution, you know, maybe we're up to a pH of 12, 13, something like that. It depends on how much you add. So this is the situation that's happening when we add a strong acid or strong base to a non-buffer situation. Any questions on that so far? So obviously it would make sense now to talk about what would happen when we actually add this to a buffer. So let's just use the buffer everybody loves to use in these situations. We'll go with our classic acetic acid and sodium acetate buffer. First off, how do we know this is a buffer? Well, this meets the definition. This is a weak acid, and this would be the conjugate base. It's really the salt of the conjugate base. What makes it the salt? It's got a sodium. Yeah. And it's basically that sodium ion. Sodium is a neutral salt, right? Not really participating in much, but just there to balance out the charge. What's really the active part of the buffer here for the sodium acetate? It's really just the acetate part is sort of the active part of the buffer. The sodium is there. It's just kind of spectator, your ion, not really participating and stuff like that. So this is your classic definition of a buffer here. It has that weak acid conjugate base. What does that mean? Well, it means that this buffer here has an acid part, and it also has a base part. And again, both of those things, the acetic acid and the acetate, are in the solution to begin with. So what happens when we have a beaker of acetic acid and sodium acetate sitting there as a buffer, and we decide to add the exact same acid as we added to water? We decided we're going to add the hydrochloric acid to that buffer. Different than when we add it to water, because we're adding this strong acid, it is going to react with one part of the buffer because it's sitting in there. Again, you have really, you know, a beaker over here that's got some acetic acid floating around. It's got some acetate floating around. So when my HCl comes in, it's going to want to do a reaction. Who's it going to react with? Well, it is going to react with, in this case, the base, right? Because they are called acid-base reactions, not acid-acid reactions, right? That doesn't make sense. So what we're going to get when we add the HCl is it's actually going to react with the sodium acetate part of the buffer, as that is barely a base. And what's going to happen here is like an acid-base reaction, double displacement reaction, however you want to look at it. We're going to get the H and the acetate coming together to make acetic acid. And we will get some sodium chloride. And a just basic sort of acid-base reaction that's going to occur. First off, any questions on that reaction there? Okay. So let's take a look at what we just did here and what happened as a result of this. Well, first off, we'll look at this over here, which is our salt. And that salt is sodium chloride, and we should remember that sodium chloride is a neutral salt, right? Which means it clearly is not going to mess up the pH. What is the other thing that we actually made here? The other thing that we made here is acetic acid. We actually made some acetic acid. Where did we have acetic acid to begin with? We actually had acetic acid in our buffer to begin with. So this always happens when you have a buffer, is when you add either acid or base to it. one of the things that you produced is actually the other part of the buffer. So when I added the hydrochloric acid here, it reacted with the base part of the buffer. But what it did in result of that is it actually made the acid part of the buffer back a little bit. So clearly the acetic acid was there to start with, which means it's not going to affect the pH. We made a neutral salt there that's not going to make the pH. But the really most important thing that happened in this reaction is actually something we don't see. And what we don't see in this reaction that we did see in the one where we reacted with water is when we look at this side, we did not produce any free H plus, right? No free H pluses, no additional H pluses floating around there. Again, just a reminder, when we did it in water, we produced a lot of H plus, right? When we added that hydrochloric acid, a ton of H plus. That is what basically caused that big shift in pH that we saw when we did it with water that's not a buffer. Here, though, when we add the exact same acid to this buffer, pretty much we don't produce any free H plus. What does that mean? Well, it means that if we didn't produce any free H plus, the concentration of H plus remains relatively constant. And if the concentration of H plus remains relatively constant, that would mean that the pH also remains relatively constant. What I mean by relatively constant is, in reality, if you had a pH meter in there and you added the HCl to this guy, the pH is about 4.74 to begin with. It would go down a little bit, maybe 4.6, maybe 4.59, something like that. It will go down a little bit because in reality, you are producing a little bit of H plus coming from that acetic acid that's being produced, but you're not producing a ton of free H plus. You're really not producing very much of any free H plus that wasn't there to begin with. But there is a little bit produced in reality, and it does go down just a tad. And we don't see these really big changes in pH because ultimately we're able to maintain the H plus concentration as being almost constant, and that keeps our pH being almost constant. Question on what happens when we add an acid to this buffer. So then let's talk about what happens when we add a base to this buffer. So we'll add the exact same base that we did to water. We're going to add some sodium hydroxide here. So if we add some sodium hydroxide, which is obviously a strong base, and again, just visually to our buffer here where we have acetic acid floating around, which is the acid part of the buffer. We have some acetate floating around, which is the base part of the buffer. When I react my sodium hydroxide with this buffer, it is going to react with the acid part. Again, acid-base reaction. So the sodium hydroxide and the acetic acid will actually react together in an acid-base reaction, really. And again, you can think of it as acid-base reaction. You can think of it as a double displacement reaction. Actually, it's sorry, this is actually in the negative here. And what's going to happen in this case is we are going to produce sodium acetate, and we're going to produce our good friend H2O, yeah, salt and water, basically. And when we look at this, let's take a look at what we just produced. Well, just like before, here we produced some water. Water obviously is not going to affect the pH, so this will not affect the pH. What is the other thing that we produced here? Well, we produced sodium acetate. And again, that sodium acetate should look familiar to you. We produced some sodium acetate. Our sodium acetate was originally part of the buffer. It's basically acetate, even though the sodium's there, but it's basically acetate that's being produced. So just like above, what we see is as a result of this reaction, as a result of adding the strong base to this buffer, we used up some of the acid part of the buffer, but we actually made some of the base part of the buffer, which is acetate in this case. And what ends up happening in that case is obviously this will not affect the pH because, basically it was there to begin with. But just like above, the important thing is actually, again, what we do not see here. And what we do not see here is we do not see any free OH minus being produced. So if we look back again at our sodium hydroxide in water, we produced a ton of free OH minus, right? All over the place. It was that OH minus that affected the pH. Here, when we add the same base to our buffer, we do not see any OH minus. So what does that mean? It means that pretty much our OH minus remains relatively constant. Why is that important? Well, that's important for that KW relationship we've been talking about. The H plus and OH minus are tied to each other, which means, again, as one goes up, the other goes down, which means if the OH minus concentration remains relatively constant, that would imply that the H plus concentration also remains relatively constant. And that would imply that just like above, if our H plus concentration remains relatively constant, I would expect a constant pH at this point. Question on what is going on here when we add a base to a buffer. The take-home message of sort of, how a buffer sort of works is because it does contain both an acid part and a base part in that solution to begin with, it's able to handle when you dump in more acid into that solution and prevent really the formation of free H plus from that acid coming in. That again keeps the H plus concentration constant, keeps the pH relatively constant as well. Also, when you add base to that buffer, it's able to basically handle the base coming in. It's basically able to gobble up all the free OH minus. The OH minus ends up in water in the case on the bottom. I mean, this is really where our OH minus ends up, right? Our OH minus ends up here in water, basically, just like our H plus up here ends up in the acetic acid. But it's able to keep that OH minus concentration from increasing and no free OH minus, which keeps our H plus concentration relatively constant and thus our pH relatively constant. Any questions on that? So let's just take a picture. Let's just take a picture, maybe. I want somewhere to write, somewhere to scribble. Let me find somewhere. Give me 1 sec. That'll work. We'll scribble here. All right, finishing scribble here. So just kind of visually what we're talking about when we make a buffer. And by the way, we use the Henderson-Hasselbalch, right? pKa plus the log of the base over the acid. This is really, the formula that we use for a buffer in this sort of situation that's occurring. What we oftentimes will try to do is make the buffer in a situation where the amount of base we start with and the amount of acid we start with are very similar to each other. Ultimately, a lot of times, sometimes almost the same concentration. And if these guys were the same concentration, that would essentially give us the pH is equal to the pKa plus the log of 1, which is 0, which means how effective is a buffer? Well, a buffer is usually effective plus or minus 1 of the pKa value. I guess I should put plus or minus 1 there of the pKa value. It sort of is like a 0.1 of the base to acid ratio. and 10 basically is sort of what that comes from. But really the buffer works pretty well at a plus or minus 1 range of the pKa value. That's also how you can maybe choose what you would want to make your buffer out of. You would want to look for a weak acid or a weak base that has a pKa value, you know, plus or minus 1 of your desired pH you're trying to make. You know, for example, if I was trying to make a pH of 4 for my buffer, I wouldn't want to choose, say, something like NH3, which has a pKa value of like 9.25. Not going to be a very good buffer. You might want to choose something like acetic acid that has a pKa value of like 4.74. That would be very close and probably okay to make my sort of buffer out of it. So pH buffers work really well within plus or minus 1 of the pKa value. It also is sort of how we choose what's a very good sort of source to make your buffer out of. But if we just visually think about what's happening here when we have a buffer, again, if we sort of make those things equalish, again, the acid and base part of the buffer. And what we see happen here is when we add acid to my buffer, what ends up happening is the acid will react with the base part of the buffer and it's going to use some of that up, but it will actually make some of the acid part. So my exaggerated drawing here, things got way bigger as well. Base part and acid part. I'm not sure why they got gianter as well. But this is sort of what happens here, you know, when we add an acid to a buffer. We're going to use up some of that base part. We're actually going to generate some of the acid part of the buffer. And, you know, it allows it to sort of work for a good period of time, right? Because you're kind of regenerating part of the buffer, even though you're reacting with one part of it as well. Same thing would happen here if we added a base to the buffer. The base would react with the acid part. And again, my over exaggerated drawing here, that means we would actually make some more of the base part of the buffer. We'll use up some of the acid part of the buffer in this case. And so we're sort of regenerating part of the buffer, even though we're reacting with part of it. So there is something that's also known as, you know, and again, this is sort of how you would choose a weak acid or weak base to make a buffer. But there's also something that's sometimes referred to as buffer capacity. And what is buffer capacity? Well, will a buffer work perfectly in every situation? And the answer is no. So what happens if you were doing an experiment and you didn't read the instructions? I'm sure that never happens. And, you know, you're supposed to go to the shelf and grab like the 0.1 molar hydrochloric acid for your buffer to add. And you decide, well, 18 molar seems like 0.1 molar. Seems pretty close. I don't really, it's not that important, the actual numbers, I suppose. So you grab the 18 molar hydrochloric acid and you dump it into your buffer. Now, your buffer is probably not made to handle that much hydrochloric acid coming in. And what's going to happen? Well, in that situation, what might happen is, if you think about our little drawing here, you add that acid that's way too much for your buffer to handle. It's just going to keep eating up the base part of your buffer until at some point you got none of it left, right? It's all going to be gone. And what happens at that point? Well, once you blow through your buffer, basically, and you keep adding that acid, you are now going to keep adding a bunch of free H pluses. And what would we expect to happen at that point? We would expect a pretty big drop in the pH, right? Because you've now blown through your buffer. because you didn't read a label. And we would expect the pH to go down a lot because it could handle it for a bit, but at some point, yeah, you're going to kind of blow right through it and it's not going to be able to handle it. And we would see at that point your buffer not being able to handle all of that acid that you're adding there. Well, let's just say you didn't, maybe misread or too badly misread, but you didn't read the instructions and you just decide, hey, I'll just keep adding base, right? So same thing would happen. At some point, if you keep adding base, you're going to continuously chew up the acid part. And if you add way too much base, it may take a lot, but if you added way too much base, or maybe again, even you grab something that was the wrong concentration, you will eat up all this acid part. And at some point, all the acid part of your buffer in that case would go away. And at some point, when you were adding that base and you keep adding, it's not going to deter you. You're basically just adding more and more OH minus to the solution. What's that going to do? Well, we would expect the pH to jump pretty high in that case because you added a lot of OH minus very quickly. So there is sort of a limit to how effective a buffer can be. It has a lot to do with the concentration of the buffer itself, has a lot to do with the concentration of what you are adding to the buffer as well. And these are things you want to think about when you're making a buffer. Is it appropriately sort of in terms of its concentration to handle whatever you're going to add to it? Any questions on that there? All right, so that's a good place to stop for now.